Today's topic is phase velocity and group velocity. Consider a plane progressive wave moving along the direction of positive x-axis, having angular frequency omega equal to 2 pi nu. Nu is frequency, and propagation constant k, it is 2 pi upon lambda. Lambda is the wavelength. Then we can write for this plane progressive wave as E equal to E0 e to the power I omega t minus kx. For this wave, velocity by which planes of constant phase moves is known as phase velocity. We write it by Vp, phase velocity. For plane of constant phase, we have omega t minus kx equal to constant. Omega t minus kx is phase. So for planes of constant phase, we have omega t minus kx equal to constant. By differentiating it, we get omega dt minus k dx equal to 0, or dx upon dt equal to omega upon k. And this is Vp, phase velocity. So phase velocity Vp is equal to omega upon k. Now we consider wave packet and define group velocity. When two or more waves superimpose on each other, we get resultant modulated wave, which is known as wave packet. Wave packet is a localized wave, amplitude of which is large in a small region and is negligibly small in rest of space. Amplitude of resultant modulated wave is large in that region in which constituent waves interfere constructively. If there is constructive interference, we find large amplitude, and amplitude of resultant modulated wave is small in the region in which constituent waves interfere destructively. For destructive interference, we find a small amplitude. We now consider a wave packet made by superposition of two waves having angular frequencies omega 1 and omega 2 and propagation constants k1 and k2. Let difference in their angular velocities, angular frequencies is very small, and difference in their propagation constants or wavelengths is very small. Difference between omega 1 and omega 2 is small, which is the difference between their angular frequencies, and difference between their wave vectors k1 and k2 is very small. Let amplitudes of both waves are same, say E0, and both are moving, propagating along the direction of positive x-axis. Displacements of two such plane progressive waves are given by following two equations. So we have these two plane progressive waves. Displacements are given by E1 and E2, E1 is equal to E0 sine omega 1t minus k1x, and E2 equal to E0 sine omega 2t minus k2x. Here E0 is amplitude, which is same for both the waves, and angular frequencies are omega 1 and omega 2 respectively, and propagation constants are k1 and k2 respectively. We assume that omega 1 and omega 2, there is difference between omega 1 and omega 2, this difference is small, and difference between k1 and k2, it is also small. Resultant displacement from the principle of superposition is E equal to E1 plus E2. Resultant displacement will be sum of the two displacements E1 and E2. So E is equal to E1 plus E2. Put the values of E1 and E2. We have E equal to E0 sine omega 1t minus k1x plus E0 sine omega 2t minus k2x. E0 is common, and inside the bracket we have sine omega 1t minus k1x plus sine omega 2t minus k2x. Now the term inside the bracket, we write it as 2 sine omega 1 plus omega 2 by 2t minus k1 plus k2 by 2x cos omega 1 minus omega 2 by 2t minus k1 minus k2 by 2x. Here we have used the formula of sin C plus sin D. Sin C plus sin D is 2 sin C plus D by 2 cos C minus D by 2. So sin plus C plus D by 2, this gives sin omega 1 plus omega 2 t by 2 minus k1 plus k2 x by 2, and C minus D by 2 will give cos C minus D by 2. It gives cos omega 1 minus omega 2 t by 2 minus k1 minus k2 x by 2. In the next step, we write 2E0 and then write this term of cos before the term of sine. So we write 2E0 cos delta omega t by 2 minus delta k x by 2. Here we write delta omega as omega 1 minus omega 2. It is the difference of omega 1 and omega 2. And delta k is written for k1 minus k2. It is the difference of k1 and k2. So this term cos omega 1 minus omega 2 t by 2 minus k1 minus k2 x by 2, we write it as cos delta omega t by 2 minus delta k x by 2. And the sine term, we write it as sine omega t minus kx. Here we write omega for omega 1 plus omega 2 by 2, which is the average of omega 1 and omega 2. Similarly, we write k for k1 plus k2 by 2. Here also k is the average value of k1 and k2. So here we have assumed that omega 1 minus omega 2 is delta omega, k1 minus k2 is delta k, and omega 1 plus omega 2 by 2 is omega, k1 plus k2 by 2 is k. This is equation 5, which represent E, amplitude of resultant wave, and amplitude of resultant wave E is 2E0 cos delta omega t by 2 minus delta k x by 2 sine omega t minus kx. Now we see that amplitude of this resultant wave is 2e0 cos delta omega t by 2 minus delta kx by 2. This is the amplitude. The term before the sine term is the amplitude. So we see that this is amplitude modulated wave. The amplitude is not constant. It depend on time t and distance x. This equation 5 represents amplitude modulated wave or a wave packet. This amplitude modulated wave is a wave packet. Velocity by which envelope of modulated amplitudes moves is known as group velocity, and we write it as Vg. So Vg, velocity, group velocity of this wave packet is the velocity by which envelope of modulated amplitudes moves. And to find this group velocity, we write for constant modulated amplitude. Modulated amplitude will be constant when the term inside before cos is constant. It means delta omega t by 2 minus delta k x by 2 is constant. And if we differentiate this, we find delta omega dt minus delta k dx is 0, and this gives dx upon dt as delta omega upon delta k. Dx upon dt is the velocity. Now we write group velocity Vg as this dx upon dt, which is delta omega upon delta k. But for the limit delta k tends to 0. So Vg, group velocity, is limit delta k tends to 0, delta omega upon delta k, and this delta omega upon delta k changes to d omega upon dk in this limit. So group velocity Vg is d omega upon dk. Phase velocity Vp is omega upon k. Group velocity Vg is d omega upon dk. Now we find the relation between phase velocity and group velocity. From equation 5, substituting the value of omega equal to Vpk. From the definition of Vp, Vp is omega upon k. We have omega equal to Vpk, and substitute this value of omega in this expression for Vg. Vg is equal to d omega upon dk. Here put the value of omega from the definition of Vp. Then omega is Vpk. We put this value here in the expression for Vg and find that Vg, which is d omega upon dk, it is d upon dk, and omega is Vpk. So we differentiate Vpk with respect to k by using formula first function differentiation of second plus second function differentiation of first. So we find Vp, it is first function, differentiation of second is dk upon dk, that is 1, plus second function k and dvp upon dk. So Vg is equal to Vp plus k dvp upon dk. Since k is 2 pi upon lambda, k is propagation constant, it is related to wavelength lambda by this formula. So dk is equal to minus 2 pi upon lambda square d lambda. 2 pi is constant. Differentiation of 1 upon lambda is minus 1 upon lambda square d lambda. Now put the values of k and dk. Here we get Vg equal to Vp plus 2 pi upon lambda dVp upon minus 2 pi upon lambda square d lambda. 2 pi is cancelled out, lambda is also cancelled out in denominator, and we get Vg equal to Vp minus lambda dVp upon d lambda. This is the relation between phase velocity and group velocity. This is the relation between Vp and Vg. Now we see what is dispersive and non-dispersive medium. Relation between omega and k is known as dispersion relation. A medium in which this omega k relation is linear, that is for which omega is proportional to k, then that medium is known as non-dispersive medium. It is clear that for a non-dispersive medium, omega equal to ck. For non-dispersive medium, omega is proportional to k. So we write omega equal to ck. C is some constant. Then phase velocity Vp, which is omega upon k, it is c. And group velocity Vg, which is d omega upon dk, it is also c. So for a non-dispersive medium in which omega is proportional to k, there is linear relationship between omega and k. We see that phase velocity and group velocity are same. So in non-dispersive medium, phase velocity and group velocity are same, Vg equal to Vp. A medium in which omega k relation is non-linear, it is known as dispersive medium. So for dispersive medium, relation between omega and k is non-linear. Omega is now not proportional to k. In dispersive medium, phase velocity and group velocity are not equal. Vg is not equal to Vp. According to equation 7, equation 7 is this equation which relates Vg and Vp. Relation between group velocity and phase velocity, relation between Vg and Vp. This is equation 8. And this is equation 7. Vg equal to Vp plus k dVp upon dk. So from equation 8, which shows the relation between Vg and Vp. Vg is equal to Vp minus lambda dVp upon del lambda from this equation 8. So it is not equation 7. According to equation 8, when dVp upon d lambda is 0, if dVp upon d lambda is 0 in this equation 8, then we have Vg equal to Vp. Vg equal to Vp, and the medium is non-dispersive. And when dVp upon d lambda is not equal to 0, the two cases may arrive. First, when dVp upon d lambda is positive. If dVp upon d lambda is positive, then from this relation we see that Vg is less than Vp. Vg is less than Vp, and we say that medium is dispersive and dispersion is normal. And if dVp upon d lambda is negative, then we have Vg greater than Vp, medium is dispersive, and dispersion is said to be anomalous. So when dVp upon d lambda is 0, medium is non-dispersive, and when dVp upon d lambda is not equal to 0, the medium is dispersive. There are two cases for dispersive medium. When dVp upon d lambda is positive, Vg is less than Vp, then medium is dispersive and dispersion is normal. We called it normal dispersion. And when dVp upon d lambda is negative, Vg will be greater than Vp, medium is dispersive and dispersion is anomalous.